And I'm live. That is cool. And today is 19th of August 2025, Tuesday. And yesterday we did some things on number theory from the competitive programmer's handbook. Like we did more than half, but the first half was easier to understand. We got stuck in some Euclidean proofs, but the progress that we did make, we do understand whatever we learned yesterday. And today my goal is to move forward and maybe even complete the whole chapter on number theory, which includes the Chinese remainder theorem, which I only know by name, and there were some other proofs, something by Robin Wilson and other things. So we will see how far we can go, but the main thing is clarity and comprehension. When I say that some topic is complete, I have to be sure that I can recreate the whole derivation, the whole proof for the formula that I'm saying is complete. And that is the main goal because we do not want to repeat things, right? If we are doing something, then we are doing it properly. And let's begin. Number theory, CS, and yep, in the title, this thing, CPHB is Competitive Programmer's Handbook, which is this book, Competitive Programmer's Handbook. It is free and open source. Yeah, open source. You can go and read it, which is cool. And first, before beginning and moving forward, we would see what we did yesterday. So, number theory, number theory, and yeah, and then we saw that there are some simple seeming problems, but they could be open problems in number theory. That is, no one knows the answer to these simple problems. So, number theory, you need to know about number theory. And there is a way, there is a thing called prime factorization. That is, you can represent any integer as its prime factors, and that will be unique for every integer. Then there is a formula to calculate number of prime factors, number of factors. Then there is a formula for sum of factors, and then there is the formula for product of factors. For number of factors, you just do this, like multiply the powers of these things, add one to them and multiply them together. And for sum of the factors, you take a little gm gp sum and multiply them for every prime number. And product of factors, you just take your target number and raise it to the power of number of factors divided by 2. And number of prime numbers, there are number of primes. Yes, we yesterday proved that there is an infinite number of primes. Then density of primes, there are a lot of primes, and in a range from n1 till n, there are about n divided by log n primes, and number of primes in a given range n is represented with this symbol pi, I guess, because pi means pi and prime are very close to each other. Then we read about conjectures. Conjectures are proofs. The conjectures are results, or like sayings, propositions which do not have proof, but we treat them as if they are true because they have not been falsified yet. So there is the twin prime conjecture, there is Legendre conjecture, and Goldbach's conjecture. I don't, maybe this one might be useful at some places. I do not know where these two would be useful. And then we went on to basic algorithms. In this part, we looked at what the equivalent of a middle point is when we are talking about multiplication. Multiplying two numbers a and b to get a number n. When you add two numbers, then the middle point lands at n by 2. But when you are multiplying two numbers a and b, then the middle point is at about n, is about root n. And you can use this fact to find factors of a number. Yep. Sieve of Eratosthenes. This is an ancient algorithm. I guess Eratosthenes was a Greek Eratosthenes was born in Libya and he died in Alexandria, Egypt in 130 BC. And he gave this amazing algorithm in which you, whenever you find, you start iterating from the lowest number in your range and go up as high as you can in your range. And whenever you see a prime, you put all of its multiples equal to 0, where 0, you put all of its multiples value equal to that smallest prime that you just found, which represents the smallest prime factor for this number. So that is cool. And then Euclid's algorithm, which is easy to visualize. Euclid gave a very elegant proof in terms of lines around 300 BC. That was crazy because he used lines to prove his GCD algorithm, because Greeks had no concept of representing numbers as we use them. Like this A, B, and C, they used lines. They had no algebra in terms of numbers. And yep, this is the Euclid's algorithm. Then totient function. Okay, this is the first thing on which we spent some time researching. So tot in Latin means all of, or complete, or full count of. And here totient function means totient of a number n is the number of co-primes from 1 to n with n. So totient of a number returns the number, the count of co-primes that you have from 1 till that given range, which are co-prime with n. And if totient, you're trying to find totient of 12, that will give you 1, that will give you 4, because there are this thing, totient of 12 will be equal to 4 because there are 4 numbers from the range 1 to 12 which are co-prime with 12. It is 1, 5, 7, and 11. And then this thing, why does this thing work? For this we used some probability mathematics to prove this, and this was very elegant, and I would like to write the basic formula that we derived. It must be here somewhere because we did wrote it yesterday. Okay, it seems to be gone, or maybe, yep, it is kind of lost. We can start anywhere. Okay, here let's say the formula that we derived yesterday was like this: totient of a number n would be equal to n into 1 divided by 1 by p1 into 1 divided by 1 by p2, and so on, with p1, p2, and then later pk, till pk, or any number till pk are prime factors of this number n. These are prime factors of this number n, and this thing can be translated into this formula here. And we also have this alpha I in this formula, but we do not have this here, which has a reason, because okay, let's derive the whole thing again. If you do this and if you try to solve this, you would get like this: p1, and let's just do it with p1 and p2 for now. So p2 minus 1 divided by p2, and let's just say these are the only numbers, only prime factors for n, and alpha 1 and alpha 2 are the powers for these p1 and p2 prime numbers to make their product equal to n. And then you divide n by p1. That would give you, and you can write n as p1 power alpha 1 into p2 power alpha 2. And then write this whole thing, this thing, same thing again here, P1. And yep, writing is, by the way, amazing, pretty amazing. P2, and then you divide this P1 by this and P2 by this P2. This seems like a H, but it is P2, and P1 alpha 1 minus 1 because we divided, and P2 alpha 2 minus 1 and into P1 minus 1. And the writing is, of course, amazing, very amazing. And yep, P2 minus 1. And you can, since these are in product, you can write them as product from I equals 1 till I equals k for all P1 to Pk prime factors. You can write it as Pi power alpha I minus 1 into Pi minus 1. And does this thing look similar? It does. This thing. But wait, I do not know what this symbol is called. I know that it is for multiplication, but what is it called? Multiplication called like multiplication summation symbol called pi represented by Greek. Okay, it is called pi. Okay, okay. The symbol is called pi. I mean, of course, it looks like a pi, so it is called pi. Nice. Hello. And then we delved into a bit of modular arithmetic. We didn't complete the whole thing. We saw why this thing makes sense, why this thing makes sense, and this thing is a little tricky because the answer for this could be negative, and why this thing makes sense, and why this thing makes sense. Then we wrote a little code for modular exponentiation. Then this thing, yeah, this was the last thing that we did yesterday. We spent more than 1 hour on this little thing. Why this thing makes sense? Why would this make sense? And if this thing makes sense, then this thing would correctly make total sense. And why does this thing make sense? Okay, I haven't revised, but I would like to see if I can derive the whole thing that we did yesterday. It would be pretty cool. Let's see. We have, okay, so the thing here is this. We have a number x and we are raising it to totient of m, and if we take its modulus with m, it should be equal to 1. That is the thing. Yep, it should be equal to 1. So why is this true? And the basic thing is m is any number m, x is any number x, and we are saying that if we raise x to the power of totient of m minus 1, or totient of m, then after taking modulus, we will get 1 as a remainder. And yesterday, while we were seeing why this thing works, we worked out a lot of things, but in the end, we skipped a few things. We were not rigorous enough. So let's today be more rigorous than we were yesterday. And in this thing, okay, so totient, as said above, this thing totient gives you the number of the count of numbers from 1 till m which are co-prime with m. And yes, here the condition is that x is co-prime with m. That is the only condition. Otherwise, x can be anything, m can be anything, and the only condition is that x is co-prime with m. And now the thing is, if we take totient of any number, let's say for our example, m equals 12 and totient of 12 is equal to 4. Why? Because from 1 to 12 there is 1, there is 5, 7 and 11, and all of these numbers are co-primes with 12. So, and there are 4 numbers, 1, 2, 3, 4. That is why totient is 4. And if we create a set, let's call it U12, that set, let's say, contains all of these co-prime numbers which are counted in the totient. So that set would be equal to 1, 5, 3 and 11. And I'm like deriving this in real time. I haven't revised this since yesterday, but this is the thing. We are calling this set which contains all the co-primes from 1 to m, 1 to 12 in our case. We are calling this set U12. And the claim yesterday by ChatGPT was this. If we take modulus of all of these numbers with m, which is 12, it is going to be equal to the number itself, because all of these numbers are lower than 12, since totient is the highest number in the totient is equal to the input number. Therefore, all of these numbers are lower than 12. And when you take modulus of any number that is lower than that number m, it is going to be equal to that input number x. So here modulus is this, and we can represent this in modular arithmetic's circular term like this. For 12, 0, 1. So this is a normal clock. In a clock, 12 things, 4, 5, 6, 7, 8, 9, 10 and 11. And if you were to represent and take all of these numbers which are co-primes with 12, these are the numbers. And the claim is that if you take any number x that is co-prime with our given number m, in this case 12, that number, no matter what it is, it will be, if we represent it in modular terms, it will be one of these numbers which are already in this U12 function. And we have an example. 13 is a coprime with 12, and 13 mod 12 does equal 1, which is here. And that is the thing. 17 is also coprime, which would give mod equal to 5. And then we have 19 is also a coprime, that would give mod equal to 7. And then we have 11, then we would have, I guess, 23. Yep, 23 is also a coprime, which would be represented as 11. So the claim is just this. X, if we represent x in terms of mod with 12, that will be represented as one of these numbers in this set. And we can make this more general, because since we know GCD of x, okay, and this proof, when this literally clicked yesterday, this was so obvious. So we are saying this is the base case. We are saying GCD of x and m is 1. That is why they are co-primes. That is by definition true. Then you can write this as GCD of x mod m, right? This is the thing we use in Euclid's method when we are trying to find GCD. You can reduce one of the numbers equal to the mod of the other number. This is the thing we do in Euclid's algorithm. And then, since this is a remainder, this number is going to be from 1 till m minus 1. This is going to be the range for this part, and we can write this as r, remainder. So GCD of r comma m equals 1. And now the only possible values for r, we are saying r must belong to this UM set. Why? Because we know that R modulus M is 1 and the UM set, this thing U12 in our case, has all the numbers that are co-prime with 12 with our number M. And since this number is also co-prime, then this must be a part of this set. And if this R is not a part of this set, then our set is wrong and it must contain this other number which is also lower than M and is co-prime of M. So this number, this X number, when represented in modular terms, we are saying X is co-prime beforehand with M, then this must be represented as one of these numbers. So that is the proof for that. And now there were a few other claims made by ChatGPT, which were, now should I forgot exactly, but yes, so this thing was a big leap when we understood this, that any number that is a co-prime with M, if we represent it modulo M in this, then it will belong to this set which contains all of the co-primes with U, all of the co-primes with M. And if we have that given, we can make a clock. If we have that given, then there was a little thing given by ChatGPT. We can multiply this UM. Yes, now, yep. I remember now. We can multiply the whole set UM by X, right? And this thing would also, let's say Ri is some member of this UM set, and if we multiply Ri by X, the claim is that GCD of this thing with M is going to be equal to 1. And why would that be true? Because by definition in the UM set, if I take any element from the UM set and take its modulus, take its GCD with M, it is by definition equal to 1. And by definition, again, if I take any this number X and GCD with M, it is also equal to 1, which means that Xi does not share any prime factors with M except 1, and 1 is not prime, so that is also cool. So no prime factors, and same goes for X. Now it should be obvious that when we multiply these numbers together, there is no other magical prime that appears which is going to be a multiple, which is going to be a divisor of M. So therefore, GCD of Ri into X M is also going to be equal to 1, right? That makes sense. And given that fact, when we multiply this whole set by X, all the new numbers that we get, this thing will be equal. If we multiply it by X, if we multiply this whole set by X, we would get a set, Ri multiplied by X, where Ri belongs to UM. And given that, now we want to prove that every number in this is unique, and multiplying by X only shuffles the number in UM. It does not introduce new numbers. We know that multiplying any number by X in this set does not the new number that you get by multiplying does not create any new numbers. It is going to be one of the other numbers in the set which is already present in the set. And now the claim is that after you multiply all of these numbers, they would just shuffle around and no two numbers would be equal. And that would help us to prove x into um equals to um. That is, this x has no effect on this um. And how can we prove that? Let's see. There was an elegant proof that ChatGPT gave yesterday. And yep, there was an elegant proof that ChatGPT gave yesterday for this thing. And that was, shit, I'm forgetting the proof. When we multiply x is a coprime of m, any number m, x is a coprime of m, and is the set of all coprimes of m which are lower than m. And the proof that ChatGPT gave yesterday for this thing, if you multiply x by all of the numbers in it is going to be equal to m, not just less than or equal to, but exactly equal. Let's say, okay, let's say we do xi into x is just a number, not not an iterator. Ri is a iterator which belongs to this set. When you multiply these, then you will get a set of prime factors, p1 alpha 1, and you can represent this whole number as a set of prime factors, p2 alpha 2, and so on. But I would have to look it up. The proof that ChatGPT gave yesterday for this thing. Uh, Bipartite GCD algorithm. No. Yeah. Example, this thing. Okay. Coprime set subset. Right. And then, yes, this thing was true. Then ChatGPT proved that these two sets are going to be equal, which was a crazy thing. Yep. Take all the numbers of take all the numbers that are coprimes to m that are exactly there are exactly of them. Call this set u. Now multiply each element of u by x mod right? Okay, we first took mod of x, so now x belongs to the set which we just proved. Because x is coprime to m, multiplication by x just rearranges the element. It does not throw in a non-coprime and it doesn't create duplicates. So that is the thing. Why there are no duplicates? Here is the proof. This is our new set, x into x multiplied by m. X is our number and a mod m, a belongs to we do not have to, okay, we are taking mod after we multiply x and a. Claim this is the same as this. Yes, that is the claim. Why? If GCD of these two is 1, which is by definition true, and GCD of these two is 1, then GCD of this is 1. So multiplying keeps us inside the coprime set. Yes, that makes sense. If two results are congruent like this and this, right? Let's suppose that it does create duplicates with a number a belonging to the coprime set and with the number b belonging to the coprime set. If you multiply both of them with x and let's say that they do create duplicates, then a should be equal to B mod, and since x has a modular inverse, makes sense since we can just remove x from this because x has a modular inverse, which we are going to get into in a bit. We can just remove x since x has a modular inverse, so no duplicates. That makes sense. And what does this mean? This means that let's suppose if I have my number x, which is co-prime with m, and I have some number r I, some number ri, and we want to prove that when I do this x multiplied by some other number rj, their mod with m, let's say it is equal, and if it is equal, we can remove x from both sides. This is x, we can remove x from both sides, and we can do that. We can remove x from both sides because x is co-prime. And why we can remove x when x is co-prime, we would get into in a bit. And now ri has to be equal to rj, and if they are equal, that means they are equal. They are not two different elements from the set. If they, after multiplying them with x, gives us the same value, then initially the numbers that we did multiply with x, they were equal. They were not two different numbers which we multiplied with x and got the same value. So that makes sense. Therefore, this set u multiplied by x is equal to um, and that means, let's actually write this. We are representing these by r x into r1, and let's multiply the whole thing into x r2 into x into r3 equals, or dot 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 till rk, into equals r1 into r2 into r3 dot dot dot. Then we can just cut all of these r's off, and on this side we would have x power equal to totient of m. Why? Because here we had a few instances of x, and how many instances did we have of x? We had the same number of instances as the number that totient function returns, because that is the number of elements in this set. Therefore, x power totient of m gives a modulus of 1 when taken with m, and we can actually verify this. And how can we do that? Let's take our m equals 12. If we take our m equals 12 and our x equals to, x has to be co-prime with 12. I guess 41 is a prime, so 41 is co-prime with 12. Yep, 41 is a prime, right? 41 is a prime. So these two are co-primes, and now the claim is, if I raise x to the power of totient of 12 and take its mod with m, it should turn out to be 1. And we can do that. 41 power totient of 12, as we already know, is equal to 4. So 41 raised to the power 4, that would be 41 raised to the power 4. That is 28,000, no, 282571761. 2825761. this is equal, and if we take mod of this number with 12, we should get 1, and we can check it. 28, 2, 5, 7, 6, 1, mod 12. It is 1. That is 1. So this thing, well, at least for this case is true, but it is also true in general because we just proved everything. So that is cool. And now we understand why this formula works, why this thing is true. Even though we just proved the whole thing, it is going to take some time to actually get used to this thing. And you can say if m is prime, if m is a prime number, then totient of m is going to be m minus 1. If m is prime, then totient of m is going to be m minus 1. And this is the same thing that you are doing in Fermat's formula. You are raising x to the power of totient of m and taking modulus, and it equals to 1. So that is cool. These are the same formula. This is the general thing. This is one specific use when m equals a prime. That is cool. And now we can move forward to what is modular inverse, right? What is modular inverse? Well, modular inverse is this thing. If you have a number x and its mod with m equals some number, right? Let's say n, its mod with m equals n. Then modular inverse, which is represented by power minus 1, modular inverse of x, modular inverse of x with respect to m would be, let's denote it by x power minus 1, x raised to minus 1. Then this number has a specific property, which is if I do x into x inverse and take that new numbers, this number's mod with m, it should be equal to 1. That is modular inverse. If I multiply x with its inverse with respect to m, then I should get 1. That is modular inverse. And this seems, now before beginning on to how we can calculate this, now we can very easily calculate this using this formula. We can just say modular inverse of x equals x power totient of m minus 1. We can write this directly as x inverse. X is a modular inverse with respect to m would be x raised to the power totient of m minus 1. That is the modular inverse of x. And we know why this works. And yes, you just have to get used to this thing. But why do we need something like this? In this book, there is an example. This thing, 36 divided by 6 mod 17. So let's say if we have something like this, 36 divided by 6, and you are taking mod of this whole thing by 17, or maybe not this whole thing by 17. I guess it is more like 36 mod 17 divided by 6 mod 17. Wait, I would have to look. For example, yeah, so x into mod x, taking modulus of that new number with m equals 1. And for example, if x equals 6 and m equals 17, then modulus of x equals 3, because when you do x, which is 6, multiplied by x inverse, which is 3, that gives you 18. And when you take modulus of 18 with 17, that gives you 1. So that is cool, that works. So those are the numbers which we call inverse. Using modular inverse, we can divide numbers modulo m, because division by x corresponds to multiplication by modulus of x. For example, to evaluate the expression, this thing. Here we have 6 multiplier, 6 in division, and we can inverse that with multiplying by inverse of 6. This thing. Okay, in this example, we had 36 modulus 6, 36 divided by 6, and you are taking mod with 17 and dividing by a number is equivalent to multiplying by its inverse. And this is not -1, I'm just, this is a bad representation, but you get the sense, I guess. This number represents inverse of 6. This new number, this number is the inverse of 6, and multiplying by a number, dividing by a number is equivalent to multiplying by its inverse, which is true in normal multiplication too. If you have x divided by y, you can write it as x into inverse of y, but that is multiplicative inverse. And when you are calculating multiplicative inverse, it is equal to just 1 divided by that number. But when you are calculating modular inverse, that is equal to this number. That number raised to the power of totient -1. So this is the same as this mod 17, and since these are in multiplication, you can divide and open the mod. So this can be written as 36 mod 17 multiplied by 6 inverse. 6 is modular inverse mod 17. And then since this value could be greater than 17, you can take the mod of the whole thing. Mod 17, and this thing would turn out, because it is 2, right? This is 2 because 17 into 2 is 34, and a remainder would be 2. 2 multiplied by this thing, inverse of 6, modular inverse of 6 is 3. We just saw it here. When x equals to 6, then x inverse is 3. This thing multiplied by 3, and mod 3 mod 17 is 3 because 3 is smaller. And you take the mod of the whole thing with 17, which is just 6. 6 should be the answer, which it is, because here if you directly divide these two, it turns out to be 6, and 6 mod 17 is 6. So that is cool, that is correct. And this is used, this, I don't know where it is used, but this must be used in some calculations where the number is getting bigger and division is not a very good thing to do. And multiplication, you might prefer doing multiplication a couple of times using modular exponentiation method that we just saw. Using where is modular exponentiation? We just saw it. Uh, Modular exponentiation, modular arithmetic, oh yeah, it is right here. You can call this function again and find the power of some number raised to another number. And why would you want to do that? Because that is how you calculate modular inverse of a given number. And now the first time that I saw this thing, I was like, what is happening? But now it makes sense because we went through this whole formula. Why this formula is correct. Even though this does not make intuitive sense right now, but over time we would get familiar to this thing and it would make more sense. So now we can continue and start reading the new things. Hi, there is live or recorded. This is live. This is live. I guess, yeah, live. And now, if m is prime, the formula becomes this. Yes, shit. This is the same thing. Now this makes so much sense. This thing makes so much sense now. After we went through this thing, why this is true, why this makes sense. After going through this thing makes a lot of sense because you could here say that you can write this whole thing. You can write what we had there was this x raised to totient of m mod m equals 1, which you can rewrite as x into x totient of m minus 1 mod m. Mod m equals 1, which you can rewrite as x inverse mod m equals 1. And this, since we are only using variables and not any specific numbers, you can rewrite this. You can take x inverse as x inverse will be equal to x raised to the power of totient of m minus 1, which is absolutely crazy. Like, and this makes so much sense now. Yeah, like going through this whole derivation makes sense. It is totally worthwhile because now this thing makes almost intuitive sense. Now let's read. However, a modular inverse. Wait a minute. However, a modular inverse does not always exist. For example, if x equal to 2 and m equals to 1, the equation, this thing cannot be solved because all multiples of 2, here x is 2 and m is 4, no matter how many times you multiply 2 by any positive integer, you are never going to get a remainder of 1. You will either get 0 or 2, and the remainder can never be 1 when m equals 4. It turns out that the value of inverse of m mod m can be calculated exactly when these two are co-prime. And does this thing make sense that inverse can only be calculated when x and m are co-primes? Because if they are co-primes, they are co-primes. If they are co-primes, then well, x into some number a plus m into some number b equals 1. And now you can, x and m are numbers, and this would be only possible when x and m are co-primes for some combination of a and b, and a and b can be positive or negative integers. That is the only restrictions. They can be positive or negative, but they have to be integers. So if you have this much minute control, the smallest possible integer, positive integer is 1. If you have this much control over the output when you are turning the A and B knobs, if you have this much control that you can even get an answer of 1, you can multiply both the sides. Let's say you want 5 on the other side. To get 5, you can just multiply both sides by 5, and you can get any number. right? But if let's say x and m are not co-primes, then the least you could do is their GCD, and their GCD in that case would not be equal to 1. If their GCD is not 1, let's say it is 4, then the only possible values you could have are multiples of 4, positive or negative. You will never get a 1 there. That is why for modulus inverse for a number x to exist with respect to a number m, both of them x and m have to be co-primes, and that makes sense. And this is how you just calculate the modulus. You calculate the inverse. If a modular inverse exists, it can be calculated using this formula. And let's code this. Let's write a function to find the modular inverse. Mod inverse dot cpp, and this will, let's say, take in a number x, and then int m, the number with whom we have to find the modulus of x. And yes, and we will have another function which will return a number, integer, and it will take in two numbers, and then we can do cout inverse of x with inverse of x mod m equals inverse x m. Keyboard positioning. Okay, and now we have to implement this function. Okay, what do we want? We want the totient, and then we want to raise this to a power of totient minus 1. And we know the formula for totient. Let's start it with 1, and we know the formula for totient is this: totient of a number n equals pi, which is multiplication of shouldn't. To find the totient, we would have to find prime factorization of that number. Okay, all of this is crazy. Okay, for I equals from 1 to k, for p I power alpha I minus 1 into p I minus 1. And to calculate this totient, we need to know the prime factorization of our number. We would have to write another function which would return a vector of pair of integers, where the first number would represent the prime number and this number pi, and the second would represent alpha I, its power. So factorize this number n. Okay, pair is not included. Include vector. Wait, not. Okay, pair is inside utility. Makes sense. And now our vector of pair of integers, let's call it response, with no specific values, no default constructor. And okay, right. For this, we would need a few things, that and that. Okay, int c equals 0. And let's say, what can we say? Now, while n, we are going to do something. I need to see the initial prime that we are going to take is 2. 2 is going to be our initial prime, and count refers to the index in which we are in our vector. So if our number n, if no remainder, when this number divided by this, the input number, when it is divided by the current number that we are at, it might be prime or might not be. Then if that is the case, then since our vector, response vector, is empty, we would have to create a new element. So res dot pushback, and it is a pair. So make pair where the first value is our prime number and the second is 0. And now while n, while there is no remainder, when I keep dividing this number by this, what we will do is res bracket c dot second plus plus increase its count. And when we get out of this, we can do b plus plus to go to the next thing. And actually, instead of this, a better thing, instead of having this p, would be a for loop int I equals to I less than, while I into I is lower than or equal to n and I plus plus. And this should work. This should work, and we can replace p with I, p with I. Yep, and we don't need this. Now this is the same thing, which this is the same thing that we used while we were writing the function for calculating factors. Now we can just return this thing, return this response, and let me just check. Do we need the C? We would need the C, and initially C is this. After this, C needs to point to the last, or we can just skip this whole C thing and just say this dot back the last number. Okay. And now auto factors of n would be equal to factorize n, not n, m, right? M, yep. We need to find the factorization of m. Now we have values for pi and alpha I. We just need to run this thing from I equal to 1 to I equal to k. And k is the size of the vector that is returned. So for int, or yeah, auto, I don't even need the indexes. So for x factors, yep. for x here, totient multiplied by equal to totient multiplied by equal to pi raised to the power of alpha minus 1 and yep, alpha minus 1 into pi minus 1. And since we need a power function, we can write a power function which would return long, which would return long, and yeah, power. It will take a number n, which we need to raise to a power of n, and a number m, which is the modulus with which the output number needs to be returned to. Now, if e equals 1, then return n and return n. Else, if that is not true, then find power long, let's call it half equal, call the power function with n e by 2 and m, and long, let's call it full would be equal to half into half mod m. And now if e is odd, return, wait, we can just do this directly, return if e is odd, question mark, if e is odd, then we need to multiply this full by another n and take its modulus with m. Take its modulus with m, right? And else, if that is not the case, then just return the full root. This should work. Yep, this will work. And this is not optimized because we are calling the same thing again and again. We do not have any memoization, so we would be calling pow with same values again and again, which is bad and we should not do. Wait, maybe no. This is the base case. We are calling one pow function only one time. So the answer for this, the time complexity for this thing would be 2. Uh, log of n. Yeah, log of n. It's cool. It's cool. So here, totient equals, since we need to take mod. No, we do not need to take mod. This is fine. We can simply multiply because totient of n is never going to be greater than n. That makes sense. Now, totient of n equals factors equals power. We need to raise x dot first to the power of x dot second minus 1. Therefore, we would need another case. If e equals 0, return 1. And our m value is going to be return remainder with m. Now we have the value for totient. Now, since we have this thing, we can calculate x raised to the power of totient of m minus 1, which is cool. Return, this should be, I guess, long is fine. No, int is fine because we will return its modulus with m. So now pow of x comma m, raise x to the power of totient minus 1 and take its modulus with m. So now this function, inverse function, should give us the inverse. Let's see. Let's see. Let's see how that works. we have written a function that takes in x and m, and it should, in theory, return the modulus of x. So blank purpose mod inverse, that was the name of the program. Run it and find modulus of 6 when we are talking about 17, and it should be 3. It is 1. Okay, so something went wrong. Something went wrong. It should be 3. It should be 3. It is. No, it is wrong. It is wrong. It is wrong. It is wrong. So why is it wrong? Let's see. What is totient of 17? Totient of 17 would be 16. Yep. And so let's see if the totient function is working. Totient, yeah. Six, 17. One, one. Let's stop this and the inverse x with m. Yep. X is the first number and m is the second number. We find totient of 6 with 17. Totient, okay, totient is wrong. Totient is wrong. So the totient function is wrong. The formula to calculate totient is this, which is correct. This is all the prime factors. And if this thing is empty, since our number 17 is a prime number, then why does this not work? If a number that we are oh, shit, this would not even run because our list of this thing would be empty. And if it is empty, then we don't have anything. In this case, 17. Okay, shit, yes, we have to include 17 also. Makes sense, makes sense. Okay, okay, that is my mistake. This function is wrong. This function is wrong. Now here, n if n is not, if n smaller, if n greater than 1, that is n is a prime number, and we would like to add n to our list. Yes, we would like to add n to our list. Therefore, it is dot pushback make pairs of n, add n, and n is appearing only once. Okay, now the gamble is this thing. I should get the correct totient this time. Now I should get the correct totient this time around. Not even the totient, I should get the whole answer. The whole answer should be correct. Now let's see. 6 and 17. and the answer that I'm expecting is 3, and it is still 1. Okay, so something is wrong, something is still wrong. Inverse with x comma m, and is the totient correct? Let's see. 6, 17, and totient is wrong. Totient is wrong. Totient is wrong. Totient is wrong. This function is wrong. If n greater than 1, which it should be at the end, and then I'm doing this thing. 17 raised to the power 0, which is 1, multiplied by 17 minus 1, that is 6. Okay, it is because I'm stupid. Yeah, shit. This thing has to be multiplied by uh, x dot first minus 1. Okay. Now we should be good to go. Now everything should be correct. P. And now everything should be correct. 6, 17, and the answer I'm expecting is 3. 3. That is cool. And let's use some some questions. How much rated is he? 1300? Are you please tell you are using? I'm using Vim, NeoVim to be exact, and so this thing is NeoVim, my text editor. It is not an IDE. Everything you see has to be configured by the user, which is amazing. So this is Vim, and this thing that you see at the bottom, it is called TMUX, Terminal Multiplexer, through which I can have sessions, which also has this amazing ability. Like right now, I can, if I wanted to do some CP competitive programming things, then I have this session running. I can go there. If I want to participate in a contest, I can go there. I have a contest session running. If I want to write something with C++, test something, I have this for lead code, for DSA, NeoVim, CSES, everything is there. Like it is amazing, totally configurable. And right now we are in DSA, which has this thing running. And let me just show you. We can go to contests. Here I have the list of contests that I have given. These things. This is just amazing. Go to DSA. Yep. Yes, the Vim subculture with tmux, the configurability that it gives is pretty cool. And now here, give me, I have written a function to find mod inverse of numbers. Give me values of x and m to test the function with. Yeah, ChatGPT saying is modulus of when x equals 3 and this is 7, then inverse is 5. Let's verify. Uh, when x equals 3 and mod is 7, then 5, that is correct. That little thing 5 is like touching this thing. I do not like that. Now 3 and 7, 5. That is cool. And with 2 and 5, we should get 3. When we put in 2 and 5, we should get 3. Let's go bigger. Let's go actually bigger. For 17 and 43, we should get 38. Let's see. For 17 and 43, right? We should get 38. We do get 38. That is cool. And also this one. For 7 and 26, we should get 15. For 7 and 26, we should get okay. It messed up. Messed up. The function messed up. Wait, there is something, some mistake, some mistake. There is some mistake. It should work here. Shit. Why was this even working till this point? Shit, that is very stupid. Shit, why was this even working? Shit. And now 7 and 26, we get 15, which is correct, which is correct. Yeah, 7 and 26, we do get 15. Now let's test this out. When our m is not a prime, when our m is a composite number. So when x is 5 and m is 12, the expected inverse is 5. Let's see. When x is 5 and m is 12, expected answer is 5. It is 5. Yeah, this is pretty cool. When x is 7 and m is 40, expected answer is 23. So x is 7, m is 40, expected answer 23. That is correct. And is my screen too small? Is it visible? Nope, it is Mac. I'm using Mac. I do not have Arch, which is bad. Like, yes, I am ashamed of it. I'm not using Linux, but one day I will. Yeah, when I have better things. So this function works. We can calculate modulus inverse. We have written a function to calculate modulus inverse, and now I would like to show you something. Since this is something that I might need in a competitive program to calculate the modulus inverse, and is there a standard library? Why is my typing slow today? Function in C++ to calculate mod inverse. I guess no, there is no built-in function, so I would have to use my own function. And while I'm doing that, I do not want to write this whole thing again and again. Therefore, I can copy this whole thing. Let me use using namespace std. And since I want to remove all the std and colon from the whole file, I can do this vim shortcut. This s %s and std. This I want to replace this empty with nothing globally. Now it is done. That is cool. All of those stds have been removed, which is cool. And this is the whole thing. I can take this, go to my vimrc file. I have a folder for all of stuff like this. I can create a new folder called mod inverse.cpp, paste this whole thing here, and go to my config file snippets.lua, in which I write my stuff for snippets for when I want to paste snippets. copy one section. Now configure this path, not print vector, but path mod inverse, and give it the correct path, which changes from mod inverse, the file that we just created, and change the variable names. Do the same thing here, vector printing here. Nope, mod inverse function, and if file mod inverse mod inverse, and yep, that is correct. If file mod inverse, then use mod inverse here, and then whenever I press, let's say mod, whenever I press mod wherever I am, that whole snippet that we just wrote should be printed at that cursor position, for which BLP mod inverse prints snippet for calculating mod inverse for some numbers. And now I can, like, this is a overkill. I just want to reload my Vim config file. Now if I do tmux attach target DSA, the file where I was, cd concepts, the folder where I am working, go to the mod inverse file, or let's say I create any new file .cpp, and I paste my boilerplate code for solving my problems, and then I press space and let me show you shit. There was a thing. No, okay, I messed up a little bit. Yeah, should I went to the wrong file. Um, yeah, here we were, and I am looking for. I had a key map for this thing called keycaster, which is not here right now. This thing, keycaster. Shift. Okay, it is Shift Command K. I forgot that. Now I remember. Shift Command K and Shift Command K. Command Shift K. See, now the key maps are there at the bottom of the screen. That is cool. You can see them. And let's say I'm here. I'm solving some competitive programming problem, and I just have to press space mod. That is the wrong thing actually. That is not what is supposed to be printed. Space mod. That is wrong. That is wrong. So I messed up a bit in my snippets file. Okay, because of this. Yes, it makes sense. This has to be mod inverse. Now it is cool. Now if I go back, if I create a new file and I paste my boilerplate code. I have a key map for pasting my boilerplate code, which is space BLP. I have everything. And let's say I want to print the code through which I can find modular inverse. So I just press space MOD. The whole thing is here. The inverse function, the long power function, everything that I need is here. I do not have to rewrite the whole thing. And I have a key map for other things also. Let me see what key maps I have. One for sieve. For sieve, I have a command, not a key map. And one for, let me show you. So let's say I need to write the sieve whole thing, sieve of Eratosthenes. I just write sieve in the terminal and the whole sieve code is here with a given range. And let's say I want to print a vector, right? And I do not want to write a custom loop. So I can write space POV. This whole code overwrites the into operator, the angle bracket into operator, this thing for a vector. This takes in a output stream and a vector of any generic type T and prints it. So that is cool. That is cool. That is just the power that Vim gives you. And now back to number theory things. Arch and code editor for Mac only. No, it is Vim. It is Vim. It is not a built-in code editor for Mac only. Yep. Yes, my GitHub repo, you can go to GitHub if you want to see my vimrc file, my name, vimrc, everything is here. And let me push these latest changes. Not as, git add everything. And I can stop this key map thing, which is, it is stopped? Yep, it is stopped. Cool. And yep, git add and git commit. And now the official, like the best message for a GitHub commit. May change and git push origin main. And you should have everything, even the thing that I just added right now, the latest changes. You can even make one for calculating GCD. GCDs are like the base sauce for cooking the number theory questions. For GCD, there is the standard standard library function which I can use, and that function under the hood uses Euclid's algorithm, and I have written TD. Let's say I think it was here mgcd. Yep, gcd.cp. Yeah, this is the function, and this is just what the standard library function also does. Just calculates this thing. This is the whole GCD function. That is cool. Can you show how you compile and run test cases? Yes, I think I can do that. If I go, let's go to any contest funnel thingy. Code forces is slow, right? Tourist. Why did I click on tourist's name? Let's say any question. And I have this thing, this extension, which is called companion. Yeah, competitive companion. And in my new Vim, I have a plugin called assistant nvim, and you can go and look this thing up. Assistant nvim, this plugin, you can add this plugin to your NeoVim, and whenever you are on a problem and your NeoVim is open, let's say my NeoVim is open here with this file. What is this? If my new vim is just generically open, I just click here on this extension, and that somehow tells my new vim that there is something happening. And I click, and you can see a file is already automatically created. And now I can use the remap, which I have defined here. With for me, it is leader CPP. You can change this to anything you want. And now inside my test case, let's say I have written some code after pasting my boilerplate. Let's say I have written some code and I want to test it. I can press space CPP and I just press R to run. But right now it is giving error because nothing happens. My test case is not taking in any inputs. That is wrong. And yeah, this is how I do my test cases thing. 21. It said I shouldn't have said that. Can you show how you compile? Yeah, yeah, done. Code forces. My code forces is Jatin Raj, my name. You- I'm only 1300 right now. I want to get to 2000. That is the goal. And now back to this thing. And how much time has it been? It's been 1 hour and 30 minutes. Okay, I want to finish this. If a module, so we went over this thing. Y, X, and M have to be coprimes for their modular inverse to exist. And we also have written a function to calculate the modular inverse, which simulates this thing, which is cool. And now, if M is prime, the formula becomes this. The formula becomes this for X inverse. And this is the same thing as what Fermat said. Pierre de Fermat. He said this thing, same thing. Right? You just divide it by X on both sides. For example, for this thing, since 17 is prime, we just raise this to 6 to the power 15, that and take its modulus with 17, and we will get 3, which we can test right now. 6 raised to the power of 15 gives us some number, and we have to take its mod with 17. That gives us 3. That is cool. So this is true. This formula allows us to efficiently calculate modular inverse using the modular exponentiation algorithm, which is the thing that we implemented. Formula can be derived using Euler's theorem. First, the modular inverse should satisfy the following equation. This is what I'm not testing, because if this is true, then what would be my modular inverse? Okay, that is a test case, that is an edge case, which I have to check for. Mod inverse. If I uh, mod inverse, if I do this, and if my x is 2 and my m is 4, it turns out to be 2, but that should not happen. I should ideally, let's say, return 0. 0 would be nice. 0 would be nice. If my this function returns 0, then I would know that no modular inverse exists. And that I can do when I am taking these numbers x and m. I need to find their GCD. And now int g equals GCD of x and m. And for GCD, I can use the library function for GCD. Use the library function for GCD. And then Why is this file read only? Mod inverse. Delete that other file. Yep, when I take this, I will find that GCD would be equal to GCD of X and M, and now if G equals 1. If G not equals to 1, then return right now 0. Now our edge case is solved. If I give 2 and 4 now, we get 0, which is cool. And now I would like to put that update into my vimrc file also. Mod inverse. And this here at the top is giving errors because it makes sense to give errors. I have not included the libraries, but when I'm pasting this in the file, libraries would already be included, so I do not need to include them here. Error here is fine. And now we move forward. This thing. Yep. Yep. On the other hand, according to Euler's theorem, mod equals 1, and this thing x raised to the power this mod x would be equal to 1. And if I do yes, cool. So the numbers x power minus 1 and x power totient of minus 1, x inverse and x totient, x raised to the power of totient of m minus 1 are equal. When you take their mod, they are equal. Well, we are only talking in modular sense, so yeah, they are equal in modular sense. Computer arithmetic. In programming, unsigned integers are represented as modulo 2k. Makes sense, where k is the number of bits of the data type. If we are using integer, it would be 32. Usual consequence of this is that a number wraps around if it becomes too large, that is overflow. For example, in C++, number of times numbers of type unsigned int are represented modulo 2 power 32. The following code declares an unsigned int variable whose value is this thing, modulo 32. So we would only take the first 30, the last 32 bytes. I guess we would miss the few bytes from the start. So this number modulo 32 becomes this, which makes sense, right? Now this thing, shit, I do not know. Shit. Okay, for this we have to do some research. For this, what are Diophantine equations? All I know about this is that these equations are of this form. These equations are of this form. And there was a person named Diophantine. Yeah, that is about it. We would have to do our research on a separate thread. Diophantine. Okay, if you cannot solve maths problems, maybe you can, like, if there is anything that you are struggling with, then read about it and practice, which is like the obvious thing. Mathematics. You can go to CACS, solve some mathematics problems, and when you solve any problem on this CACS thing, like I have solved only one problem related to graphs because I am right now practicing graphs. So after solving a problem, you can go to Analysis tab in CACS and see what the actual solution would be. In this, when I solved this, after taking the input is like this. Input is like this, where we have to treat these dots as one nodes, and we have to find how many sectors there are. And by sectors, wait, clique, yes, cliques. How many cliques there are, and a clique in a graph is defined as, no, shit, no, clique is not the right term. This graph is not complete because these two nodes are connected, but they are not connected to these. So all of the nodes are not connected to all of the nodes. And what is the specific term that you use in a graph, which can be found out here in this book? Graph terminology: nodes, edges, graphs, path, cycle, simple, connectivity, components. Yes, components. The connected parts of a graph are called its components. For example, in this graph, this is one component, this is another component, this is the third component. So in this question, I have to find and return the number of components. And what I was doing, I created, let me show you, and I didn't know any of this before reading this thing. So I went to this book because I had to practice graphs. And here I read about representation, graph representation, and I converted this whole thing into an adjacency list. And after doing that, I used DFS, which I just read about, DFS and adjacency list, to solve this problem. And I did got it right. In the first try, I got something wrong because of a edge case. I was not considering a single floating node as a component, so that was the wrong thing. But then I fixed it by creating a self loop on that node. And then I went to analysis, and there I saw this person is not doing that. This person is not creating an adjacency list. He or she is directly applying the DFS on the grid, which is crazy and which I will implement later. That is cool. That is how you learn. You go and read and you solve problems. Is there a way to improve maths, like some book I should read? And I mean, for maths in general, for competitive programming, this is the book. Go there and, like, currently I am reading about number theory. You can go and read about number theory, and like if there is some topic which you do not understand, like yesterday, I did not understand about the totient function, this thing, and we did a lot of research live on a stream what this thing means, right? And today we are going to do research on Diophantine's equation, which I just want to get on with. Yeah, here you can see what the thing is, and then you do your own research, either ChatGPT or there is a book, Concrete Mathematics by Donald Knuth. This has all the mathematical topics that you would need if you are getting into computer science, but this book you can use as a reference book, not as a front to end reading book. This is only a reference book, and do not beat yourself with a hammer if you do not understand some things in this book, because you will not understand some things in this book. Things take time. And now I would love to get back to this thing. Bro, can you please give tips for C++? How do I start learning it? If you are a total basic beginner and you haven't coded anything, then I would say do not start with C++. C++ can be scary and can scare you. It can be very scary. C++ is scary because it is very complicated. You can go and see uh, the C++ programming language by Björn Stroustrup, the creator of C++. And this is the book which I refer to, or I am reading right now to understand some topics in C++. And this book is 900 pages long. It is longer than this. Which version is this about? The one that I have is the 4th edition, so this one is older. This is the 3rd edition. The 4th edition has 1400 pages, so C++ is very complicated, so you should not, Python, so you can go here, learn X in Y minutes, and read about C++. Read some things like how a function is formed, or maybe a better thing would be to go to the C programming language. Shit, that is the C++. This is the book that I have. The C programming language. I think. Shit. This is written by, this is the one, by Brian Kernighan and Dennis Ritchie. Dennis Ritchie created the C programming language, and he also created Unix along with Ken Thompson. So this is the book, and Brian Kernighan is their very good friend. He writes a lot. You can start with this book and read about C, and there are also exercises at the end of chapters. I think there are exercises at the end of chapters, and yeah, and so this is what you should refer to and get good at C, and then you should hope to get good at C++ because C++ is very complicated. Yes, there are exercises. So you should start first with C and then with C++. And is Windows good for C++? I could never set up a GCC with VS Code. Well, you have to understand what things are wrong, and yeah, Windows is fine. Windows is fine. You could use dual boot and start Linux in your Windows, which is cool. Yeah, you can start Linux, dual boot, or WSL, Windows Subsystem for Linux. I think it is a VM. Okay. Uh, is WSL VM. While Windows Subsystem for Linux utilizes a lightweight virtual machine and WSL version 2, it is not a traditional VM in the sense of something like a virtual box. WSL is designed to be tightly integrated on Windows. So yeah, you can start WSL and start using Linux. That would be cool. And the quicker, the earlier you do it, the better it is. And you are currently at 700, you can grow. Just do more questions. And at if you are, you are at newbie rating, reading maths and all of that does not help a lot. Solving problems helps a lot. So you should solve problems at your current rating, a lot of problems. You can go and look, this is part 51. You can go and look at part 1. There, I didn't even know how to take input while solving a problem. So that I was very noob when I started in part 1. So yeah, you just grow over time. Now back to this thing. Diophantine equations. A Diophantine equation is an equation of the form this, where ABC are constants. ABC are constants and the values of x and y should be found. Okay, this much makes sense. And each number in the equation has to be an integer. Okay, all of these are integers. For example, one solution for this equation is x equals to 3 and y equals to -2. They have to be an integer. They can be positive or negative. That makes sense. 3x, 5 into 3, 15, minus 4, it is equal to 11. Cool. we can efficiently solve a Diophantine equation by using Euclid's algorithm. This is the part which I do not completely get. It turns out that we can extend Euclid's algorithm so that it will find numbers x and y that satisfy the equation this. Okay, and a while ago I said that if you have something like this, then this equation can only be solved if your C is a multiple of your GCD of A and B, which are constants. So if you can solve for this, you can just multiply your both sides with some number. Because C is your multiple of your GCD, you can just multiply both the sides with some number and get this number equal to your GCD. A Diophantine equation can be solved. Okay, so this guy is saying to solve something like this, we can solve something like this using Euclid's extended algorithm. Okay, Euclid's extended algorithm. Diophantine equation can be solved if C is divisible by GCD, that is C is a multiple of GCD of A and B, and otherwise it cannot be solved. Okay, otherwise it cannot be solved. That makes complete sense. Now the question is, how can we solve something like this using Euclid's algorithm and let him cook? Everything is here. As an example, let us find numbers x and y that satisfy the equation this. Okay, this is our problem statement like this. And then the equation can be solved because GCD of both of these numbers, yeah, for GCD for 39 and 15 is 3. 3 divides this and this is 3, and 3 is a divisor of 12, which is represented by this vertical line. When Euclid's algorithm calculates the greatest common divisor of 39 and 15, it produces the following sequence of function calls. Yes, yes, that is what we do. GCD.cpp, that is what we do. GCD A B calls GCD A remainder B with B on the other side. Well, the order should be a bit changed, yeah, but this order is also fine. This is also fine. Oh, this is not fine. This is not fine. This is uh, B and A remainder B. This is the thing, because we would like to have the bigger number on the left and the smaller number on the right, because we are taking modulus with the number that is on the right, that is the smaller number. So if you would call this with 15 on the left and the remainder on the right, then 9 on the left and the remainder on the right, then 6 on the left and the remainder on the right, and so on till we get the number on the right equals to 0. Then the number on the left is the remainder, is the answer. That is what we are checking. If not B, if not the second number, then return the first number. Okay, this corresponds to the following equations. 39 minus 2 into 15 gives 9. That is correct. And then we can write that is correct for this GCD. And for this is the thing. 9 into 1, subtract that from 15 and you get 6. Okay. And then for this 9 and 6, multiply 6 by 9, you get 3. Multiply 6 by 1, subtract that from 9, you get 3, which is correct. And then you could have written 6 minus 3 into 2 equals 0 till we left this equation. Using these equations, we can derive this thing. So we have somehow, using this, solved this thing, which is equivalent to solving this thing. And if we have solved this thing, then we can always solve this thing. by multiplying the equations on both sides with some certain number, integer. Okay, so what we have to figure out is how to get from this to this and multiply the result on both sides by 4, we get 12. So let's read the whole thing first. So our solution to the equation is x equals 8 and y equals minus 20. A solution to a Diophantine equation is not unique. Yes, it is not unique. Okay, it is not unique because we can form an infinite number of solutions. We know if we know one solution. If a pair x and y is a solution, then all the pairs x and y is a pair. And then if I multiply this with k is an integer, multiply b by k, and b is the second number somehow, and I am dividing that by GCD. What would that give me? GCD is the smallest number that I can have, and multiplying k by b gives me the extra bits which are a part of b but not a part of a, right? And then I'm multiplying those extra bits with k and adding that to x, and I'm doing subtracting something similar from 1. Okay, we will get to this formula later, but how can we convert this into this? That is crazy. Okay. Now we have to do some mathematical equation thingy. Yeah, cool. Shit, I can copy then the whole thing, I guess. Cool. That is cool. So we have this thing. We have this thing, and from this we are here we have x and y. No, we have a and b. A equals 39 and b equals 15. Now we want to find a solution to ex plus by equals some number c. And if we put in the values for our cases, and also c in our case equals 12. Well, let's first go to their GCD, which is 3. Right? We have to find this for GCD of A and B. Now, we want to solve for this thing. Given these facts, let's put in the value of A and B. A is 39, not 3. Oh, that 9 is too far ahead. So A is 39, X plus B is 15Y. 15y. We want to find values of x and y, so that this thing turns out to be GCD of a and b, which is 3. We have 3. We have this and this. So we can write these two as 9. Okay, let's try to do this. 39 minus 2 into 15 equals 9. That is our one thing, and we can use this equation to rewrite 9. Yes, I think, yeah, we can do that. Because even if this number is a bigger integer, except like something other than 1, then we can multiply this whole equation by that number to make this thing equal to this thing. And when we have done that, we can here see 15 minus 6 equals 9. which is obvious, like 15 minus 6 is equal to 9. But yeah, so 39 minus 2 into 15 equals this thing, 15 minus 6. And okay, 15 minus 6, we can take this 15 onto the other side, and we would have 39 minus 3 into 15 equals minus 6. And from this thing we can see that minus 6 equals 3 minus 9. Shit, that is bad. That is bad because we now have 9 again. We do not want 9 to be back here. I think, therefore, we should go from the bottom up. We should go from the bottom up. So, okay, we should go from bottom up, removing every number except the GCD and our target numbers and our values of A and B. I cannot remove this thing. Okay. Now we will go bottom up. 9 minus 6 equals 3, or more formally 1 into 6 equals 3. Now we want to substitute this and this. Since this number has a 9 inside, so we should substitute this first so that we can group these 9s together and substitute them together. So now we will have minus, instead of minus 6, we can write 15 minus 1 into 9. But this is minus 6, so the signs would switch, but not. We are writing it inside the bracket. So 15 minus 1 into 9, which is just 9. 9 equals 3. And this is not a 6, this is a opening bracket, right? This is an opening bracket. And then after this, what can we do? After this, we can bunch up these 9s. Yeah, this would become 2 into 9 minus 15 equals 3, which is true. 2 into 9 is 18, 18 minus 15 is 3, which is true. And then we would like to substitute this 9 out because we have the GCD. We have the GCD and we also have one of our A and B. This is the only outsider. We want to remove this. And to substitute this, we can use this equation and multiply both sides by 2. 2 into 39 minus 4 into 15 equals 2 into 9. Hmm. Okay, feel like I'm speaking too much. So now we have value for 2 into 9, which is this thing. We should be able to substitute this. 2 into 3, 9 minus 4 into 1, 5, and the rest of the equation from before, minus 1 into 1, 5 equals 3. And now we can group these things together. 2 into 39 minus 5 into 15 equals 3, which is the exact same thing that they did use, right? 2 into 39 and 15 into minus 5. 2 into 39, 2 into 39 and 15 into minus 5 equals 3. That is cool. And since we were solving for 12, we can multiply both sides by 4. Into 4 on both the sides. And we would get 8 into 39. And for this, minus 20 all this. Minus 20 into 15 equals 12. Therefore, our x turns out to be 8 and our y turns out to be minus 20, which is correct. 8 and minus 20. Okay, now given that fact, how can we write this in code? That is the thing we need to figure out. How can we write this in code? Most time at EVH takes to improve. What book is it? This one is blurry face. This one is called Competitive Programmer's Handbook. And the amount of time it takes to improve yourself is fixed. Asking for how much time it is going to take is not going to change the time. Right? It might take years or months depending on how much time you are actually given. And now, so we know as human beings how we can convert this into this, but how do I tell my computer to do this? I can write a function which will take these numbers a and b and solve for this number c, which in turn can call another function which would take in a, b and solve for their GCD. This thing. Let's see how we can do that. A Diophantine, pentene, Diophantine, pentene dot CPP. Right. We would have equation for, and what it should return a pair of numbers, that is for x and y. My bad. Should return a pair of numbers like integers. First one, let's say, is going to be x and the second one is going to be y. Mhm, mhm, mhm. Okay, shit. That makes sense. That makes sense. Okay. Extended Euclid. It will take in A and int B, and it will not take in the GCD. Well, GCD will be calculated on spot. GCD for A, B. Now I need to solve something like this. X A into X plus B into Y equals GCD. Uh, A comma B. Make this solve something like this, and how are we going to go about solving it? Before I do that, let me go to the washroom and I will be right back. Yo, hello. It is what it is. Yes, it is what it is. Be right back. I'm back. All the very best for your journey to reach 2000. Prove your point, man. Yep, I will. Yep, thank you. I will reach a rating of 2000. And yeah, I will reach a rating of 2000. Now, I think we should use our custom GCD function because we need to keep track of all of this. And if that is the thing, then since I need track of all of this, then I should use take a data structure and I will pass it on to my custom GCD function. It should not be called a GCD, it should be called something else because that GCD could mess up with the actual library GCD function. And what will this do? This will, first of all, this should return GCD. So integer, it will return an integer, and let's call it extended GCD, and it will take in A and B at least. And what is going to be the data structure that I can store? I can just keep track of these numbers, right? If I know these numbers, then I should be able to recreate this thing because I can always divide this number on the right with the number on the left. So I can use a vector of pairs for this. Integers and yeah, it will be called history, right? History makes sense. Include vector and here int g. Wait, okay, now I am deciding between should I just first of all find the GCD? No, I will just keep track of it. Yeah, makes sense. So I will create a vector uh, pair int called history, initially empty, and then I will call the GCD would be equal to G extended GCD. And wait, I think I saw extended Euclid. There is a library function for this? That is cool. What does this do? Wait, there was a key map I can use for jump to definition. Okay, there is a key map. I forgot. It could use. Okay, let's get back to our case. We will look into what that function is later. Extended G. I am very stupid. I am very stupid. Extended Euclid is right here. This is the thing that it was suggesting. Okay, that is very bad. And pass history to this. And this function will change the history itself because I'm passing history as a reference. I'm passing history as a reference, therefore it will be passed as a reference, and whatever change I make to history in this extended Euclid method will be the change it will reflect in my own personal history. So that is cool. And then here, extended Euclid. Now I need to make these calls and then work with that. So first of all, history dot pushback make pair. I can add A and B, and then call, like that should be my first instinct, and then I will check if not B, return A. That is the basic method. Else, if that is not the case, then I need to call the GCT function again. Extended GCT function. GCT with B here and A remainder B here. And also my history. And not just call it, return it. Okay, that should work now. Okay, that should work. Let's see if it does work. And we can write a custom, we can overwrite. Okay, now we know if we want to print something, let's say our G, the GCT that we just found, we can pass this into cout just like this. But if I were to do this with history, I will get error because cout does not know what to do with a variable type like history. But we can fix that. We can write here our own custom implementation, which will overwrite this thing, and our compiler would know what to do if a variable of type history is being passed. And how is that done? That is done by OStream reference will be returned by operator this, and it takes in OStream reference, let's call it OS, and it also takes in vector of pair of integers, which will be called, let's say, we can call it history or anything we want, and at the end return OS. But before that, if history, if history dot size, if it has something, then do this thing. Else OS takes in empty brackets. But if there are some numbers in history, then for auto x, which is pair of integers, auto x in that history, we would like to add them in. But before that, OS should take in a single opening bracket, and after that, for every pair that we see, OS will get single opening bracket, then x dot first, then a comma, then x dot second, then closing bracket. And yeah, that should be it. No, I would also like to have some space. Yeah, I would also like to have this thing and a comma. A comma. Would a comma? No, no, no. I would not like to have a comma there. So, okay, I'm just now fixing this for edge cases. I know at this point that I do have at least one thing in my history. So I can do this and replace x with history 0. I'm going to put out the first element like this, and then we would iterate for int I equals 1, I less than history dot size I plus plus, and let's see out OS would get, before anything, it should get a comma. A comma is nice. A comma is nice. A comma and a opening bracket, and then history bracket x dot first and then history bracket I dot second, and then a closing bracket. That should be enough. And then at the end, OS gets a closing rectangular bracket, and in both the cases, a new line at the end. What this will do, this will now this is not giving error when I'm passing C out history into this thing. This is not giving me any error, so that is good. It's not giving me any error, and let's say this function returns a pair, yes, for x and y. Okay, return make pair g. Now cool. And in main, and we would like to have custom values a, b, c in a, b, and call our function, and take their GCDs. So pair and in response equals extended extended Euclid method on A and B, and that should be enough. And with this, you that what was the name of the file? Diophantine. Okay, my bad. Diophantine. What I am expecting to see is something like this, which records everything up until this. So let's see. I should get 39, 15, then 15, 9, 9, 6, then 6, 3, and till 30. That is what I'm expecting to see when I pass in 39 and 15. Let's see. And 30, 39, and 15. That is what I see. This is cool. It is working. 39, 15, 15, 9, 9, 6, 6, 3, and 30. That is cool. This is working. Okay, so we have all of this data. Now we should be able to reproduce this equation from this data. From this data, we should be able to reproduce this equation, and we would have to see how we can do that. In the age of AI, how do platforms like Codeforces ensure participants are not cheating? I think yes, they have some system in place. That is why yes, they have some systems in place. That is why just after when you finish the contest, you have some rating, right? You get some ranking, but then when the official ranking comes out, your ranking goes higher, like higher in the sense that it becomes a smaller number because some of the cheaters were kicked out of the contest. And the method that they use is, I guess, how good someone was relative to how good they have been in the past, and also if it took them like if a person did all of the questions and the time it took them to do the first question was 1 hour, so maybe they might be cheating, right? Hello, hello, I saw hello. It takes time to get the chat here. Yes, I saw it. Yes, hello, hello. Because there is, I guess, more than 6 seconds of lag, around 10 seconds of lag, quite a bit of lag. Now we have this data structure. We want to convert this into something like this. I know that the first two values are the inputs that I gave my function. This is what we have, and we have to work with this. We have to work with this. Okay. I also need, okay, I know that I need to preserve 39, 15, and 3. I would know this just by looking at the first pair. I would know to preserve the first pair, and also looking at the last pair, whatever the non-zero value is in the last pair, I would preserve that also. And then if I begin from the second last pair, let's say I begin from the second last pair and I have a running counter for x and y. Let's say this is purely testing. I don't know what is going to happen. Let's say we have a counter for x and y, and we would change our a and b beginning from this thing. We will treat 6 as our a and 3 as our b. I think we should not do that. We should, we can do that. We can do that because we would always preserve this number, this b number, and we would be replacing this 6 with this b every time. With a, we would be replacing a, keep replacing a with b. Okay, so at the start, we would have a equals 6 in this, and b equals 3. And we want to replace a with b. We can do that, and we do not care about the remainder. We would just, no, it is in this case the addition of the two things. No, I guess I need knowledge about this thing, and only then can I replace. Okay, so I start iterating from this set? No, no, I do not start iterating from this. I do start iterating from this actually. And yes, I'm figuring this out right now. That is the whole deal. If you cannot do anything, figure it out. So here, let's say we start with a equals 9 and b equals 6. And I would like to change this 6. Can I change this 6 right now? Yes, I can change this 6 right now with 3. With 3. So I can keep a counter of the number that I had. Okay, I would have g equals 3. And do I always know that I can change this number with g? I can always change this number with g because that is g by definition divides all of these numbers which are here. G by definition divides all of them. So I will have g, and I will change this with g, right? I will change this with g. Oh, yeah. What is the equation that we have? Here in this we have 9, 1 into 9 plus 1 into 6, or like minus 1 into 6 equals 3, right? How do I tell my computer to go up and find values of x and y? And okay. Mhm. GCD is 12. GCD is 3. If I start my A at 9 and B at 6, GCD is 3. And in the next case, I know that I will not have this b. So can I replace this now with 2 into 3? Let's say I do that, right? I do that, and no, I do not want to do that. I do not want to do that because I am multiplying my GCD with some number. I do not want to do that. I do not want that to happen. Yep. Yes, this is the base equation that I begin with. Yes, okay. Okay, that makes sense. This is the base equation I begin with, and I would like to replace these numbers. And the equation that I have before that would be 15 minus 1 into 9 equals 3. And here I want to replace 6 and 9. Okay, I would like to replace 6 and 9. Can I write these, and what did I do above? Then I began with this, and I wrote this 6 as this whole thing. Makes sense. Makes sense. This right number is always in negative. Okay, that is one thing. The number on the right is always being subtracted from the number on the left. From the number on the left. And right. So when I have this, let me erase. I guess we are getting somewhere. So when we have something like this 9 and 6, let's say we begin there at 9 and 6. Let's say we do begin there at 9 and 6, and then we have 9 and 6, some domination of 6. When I subtract that from 9, I get the GCD. I know that right now, right? And then I want to replace this 6, and I know that 6 equals to something like this. In this case, it is exactly equal, but in a general case, 9 multiplied by some integer would be equal to 6. And here, I do not have any number that is being multiplied by 6. It is 1. So I can replace this here. Therefore, this is bad. Storing them as a pair would be a bad thing to do. I cannot store them as a pair because now I would have, I can, shit, I can store them as a pair. I can store them as a pair and keep updating my x and y values. Yes, shit, okay. Okay. This is the thing that we had. Okay, this is the thing that we had, and let's say we begin with A and B from, let's say, okay, we will figure out how we get to this exact number later. But let's say we begin from here, and I will keep updating x and y values. And I always need to make sure that whenever I multiply my x with A and add that to the product of B and Y, that always should be equal to my GCD. That is my invariance that I will keep, and I will keep making my A and B bigger and bigger till I reach this. Then whatever values of x and y I have, that would be my answer. Okay, so how do we do that? Currently, whenever I have a value of A and B, what I should do is, since this thing, for this thing, it is always given to be true that A is greater than B. right? That is how we begin in our function. So we can have a into some number x minus, we can take initially x equal to 1 and y initially would be equal to 1 in this case. In this case, it would be equal to 1. Yes. So let's say I will have a loop which would start with this state. That would be the state which my loop starts with at this index. And then I need to go there. I need to replace my a and b with 15 and 9. How do I do that? To do that, how do I do that? To replace my a and b with 15 and 9, I know what I need to do is replace this 6. Replace this 6 with 15 and then swap them and swap the values of x and y, right? 6 with 15. Yep. So to make with 15 and 9. So from this equation, from 15 and 9, I know that some multiple of 15, let's say x multiplied by added to some multiple y of 9 gives me 6, and I would like to replace 6 with this number and update these x and y's respectively. Let's call this x dash and y dash. So how do I find this? Given two values like this, how do I find this? Uh, all I do is I take this value here and I divide that by this value on the right. That would be, okay, so 15 by 9 gives me 1 in computers. That is how division works. This gives me 1. So I can increase 9's count by 1, which is x right now. I can make this one, and y would always be 1 until the very end. Until the very end, y would be 1. So given this scratch equation, my new x and y would be something like this, right? Right. And I can replace this b with my new value of b, which is 15. And now, since my invariance is to make a always greater than b, I need to swap all of these values. So the above value becomes 15, and here also they will be swapped. The above value a becomes 15 and the lower value becomes 9, and here comes 1, here comes 2. That is cool. And now move on to the next pair. Yes. Move on to the next pair. We have our final boss, 39 and 15. 39 and 15, some denomination of these two, it gives 9. So we need to replace 9 with this thing. And how do we do that? We do that the same way that we did before. 39, this number, divided by this number, 15. This gives 2, and whatever this is, we add this to our x, add 2 to our x, and we can replace and do our replacing things. Replace this 9 with 39 and now swap this whole thing. This is 3, 2, this becomes 2, this becomes 3, and this becomes 39, and this becomes 15. And now we have our a and b and x and y. It was it 2 and 3? Was it 2 and It was. No, shit, it is 5. It is 5. It is 5. So we went wrong at some point. 2 is correct. 2 is correct. But the other thing is not correct. We lost our invariance at some point, I think. So first we had our A equals 9. This like literally looks like 9. A equals 9 and B equals to 6, and my phone is at low battery and my laptop is also that is very stupid. My phone is now charging, but my laptop is going to die in a while, so we should do fast. Current rating is about 1300, and on what? CF. I am Indian. Z, Mr. Z. Okay, given this, what do we do? Yes, we began with these values. Then let's retrack through all the states that we went through. Our A and our X and Y values at the start were 1. Y was also equal to 1. This is 1. This is 1. And A became equal to 15 and B was equal to 9, and that is where we messed up. That is where we messed up. I guess at this point we messed up. We actually messed up. We made our x equal to 1 and our y equal to 2, which is absolutely wrong. It's wrong. It's wrong because this does not add up to our GCD. This literally does not add up to our GCD because we are supposing that we are always, this thing is always negative. That is what we are supposing. And we are supposing that this thing is always positive. So this would turn 15 minus 18. That would return in minus 3. We want plus 3. So how do we indicate signs? I think when we swap these values, we change their signs because of the swapping. Because of the swapping. Because since before the swapping, when we were in our live state, we had A equal to 9 at some point and B equal to 15 at some point, and at that point our x was equal to 2 and our y was equal to 1, which was correct because 9 into 2 minus 1 into 15, that does give us 3. So when we swap them, we change their signs. That is cool. So when we swap them, we change their signs. Removing. Yes. So when we swap them, we change their signs. That is a cool thing. Okay. So let's say, yep, we change their signs and these are their new signs. Then our A and B were updated. A became, okay, when they got updated, it came out to be 2 and our X at that point was 1. So 1 plus 2, or do I add it to Y? I added 2x, and after this my x would become plus 1 plus minus 1 minus 2. No, I have this. Then I saw that I can replace Makes sense. Okay, okay. Then I saw that I can replace this 9 with 15 and 39. Yes, this 9 with a 15 and 39. So somehow 9 equals some combination of 39 and 15. And for this, how much of 15 would I need? Negative, negative of 15. Okay, this makes sense. This is plus, by the way. No, this is also minus. This is also minus. This is also minus. And when I do this 39 divided by 15, I get 2, which translates to minus 2 somehow. Right? No, no, no. That would be wrong. Shit. Okay, I am unable to figure this out. But we have to figure this out. Or we like do not actually have to figure this out. We can look it up how people do implement extended Euclid algorithm. It has been 2 hours and 46 minutes. Okay, I want to see there is something that I'm missing. Let's start from scratch. This is what we had. This is what we have. And we begin. Okay, we have to set up our invariance correctly. At the starting, we let's say we start with the last thing, right? A equals this, b equals 0, right? And x equals 1 and y equals 0 or minus 0, right? And the invariance is this a into x plus b into y at any point should be equal to GCD, and we will keep make we will at the end should have a and b equals to the values that we started with. Now I see that I can replace this value with 6. No, I cannot do that. I can change this 0. I can somehow some combination of 6 and 3 will give me 0. And whenever I'm changing, what do I have to make sure? I have to make sure that whatever number I replace b by, that should not change this side. Okay, makes sense. Now, if I have 6 and 3 and I need to represent this like this. So I see 6 divided by 3 gives me 2. That is, I need 2 3s and 1 6. So since I need 2 more 3s to represent this 0 and 1 6, I can add 1 to this value, whatever y's value was. I do plus 1 here and I do plus whatever this value is here. So plus 2, x becomes 3, and b I have written as 6 now. Now, does this add up? This does not. This does not, because here I need minus 3. So this would be minus 2. So this should be minus 1. And that does actually makes a lot of sense, because now we do our swap thing, and Like if I do at this point a, which is 3, 3 into minus 1, 3 into minus 1 plus 6 into 1, that is 3, the GCD. So that in our invariance is still here. And now I will see the smaller number, whatever the smaller number is, and go to the place before it. Like since right now we were here, we used this to replace 0. Now we will use this to replace whatever the smaller number is, right? So now a is the smaller number, and we can replace, we know that 3 equals some combination of 9 and 6. And given this, we can solve this. 3, when we do 9 divided by 6, I know I need minus 1 of 6 to get to 9. Okay, this was equal to 1, so this will turn into 0 somehow, and this will turn into 9. I need 1 of 9 and minus 1 of 6 to get 3. Mm, That does not seem right. That seems to be wrong. Because 6 is plus 1. At this point, I have one copy of one positive copy of 6, and I can write 3 equals 1 into 9. 3 equals 1 into 9 plus 6 plus 6, 6, 6, 6, 6, 6 minus and minus 1 into 6. That does give me 3. That does give me 3, but it does not expand. So I want my A to be equal to 9 now, and B would still be 6, and X would get the new, that this number shows me how many 3s I had. Shit, okay, shit. Makes sense. Makes sense. Okay, so whatever this value is and whatever this value is, minus 1 and plus 1, I multiply it with whatever amount of C's that I had. So this becomes minus 1, this becomes plus 1. And now I change this x value to be equal to this new value, which is minus 1, and this y value gets added, this one value, which y was originally 1, now it is 1 plus 1, 2. And if we do the maths, 6 into 2, which is this, 6 into 2 minus 9 into 1, which is 9. That does give us 3. 12 minus 3 is 3. 12 minus 9 is 3. That is cool. Now we go on to our next number, which is 15 and 9. So now we see that the smaller number is 6, and we know that we can replace 6 with some combination of 15 and 9. How much? 15 by 9, new this thing dash, let's call this x, let's call this anyway, n equals this thing, which is 1. And originally I had 1, 2 of 6's. So I multiply. So this equation becomes 6 equals 15 minus 9. And here I have 1 of 15 and minus 1 of 9. And I had 2 6's, which I would like to replace. So 1 into 2 is 2, and 1 into minus 1 is minus 1, into 2 into minus 1 is minus 2. And now I have minus 2's of 9. So I add this other number to this number, which makes this x now equals minus 3, and a is still 9, b becomes 15, and this thing will be replaced by this new number, which is 2, which is 2 in our case. And if we do the maths, we should have 30 minus 27, which is 3. We just have to move one more step. We see that the smaller number is 9 here, and we have one element remaining in our data, and somehow 9 is a combination of 39 and 15, which we can write as 9 equals 39 minus 2 into 15. By dividing 39 by 15, we get 2 is 39, and we need 1 of 39 and minus 2's of 15's to represent a single 9. And how many 9's did we have? We had minus 3 9's. So this is going to be multiplied by minus 3. This becomes minus 3, and this becomes plus 6. And whatever the count we had, now I need minus 3 of 39. So now our new a becomes 39, and x becomes minus 3, and b is already 15. We need to add 6 to b, and originally we had 2. So now y becomes 8. Is that correct? I thought it was 5 or something. Minus 5 and 2, 39 of 2 39s and minus 5. Is this going to work? Okay, let's see. 8 into 15 is, what is it, 120? 8 into 15 is 120, let's say. And then I have this into 39, which is actually 117, and this does give 3. So using our algorithm, we found another answer which does work. That is cool. That is cool. Sir, do not call me sir. Sir, I am in 11th grade and wanna prep for Zio. Where do I start? I need no NT and combinatorics. What would you recommend? What is Zio and combinatorics? If I were to start combinatorics, which I need to start because I do not know about combinatorics, art of computer programming, this thing, and we just have to implement this thing. That is the only thing remaining. In this art of computer programming, there is whole thing on combinatorial algorithms, but this is too comprehensive. So maybe some beginner to combinatorics, introduction to combinatorics in Urdu. You can just look stuff up, right? See here we have some things. You can read this, and you can watch some YouTube videos. Just like that is the thing how you do stuff, right? And we now need to write this algorithm. Okay, this thing, after calling this function, our history is fulfilled. Now we need some values of our a dash and b dash and some running values for x and y, which we will return. So int x comma y comma a underscore a underscore and b underscore. and we would like to initialize them, and we will start iterating from the second last loop. So for int I equals history dot size -2, because we are going to iterate from the second last loop, I greater than equal to 0 and I minus minus, right? And what are going to be our initial values? A dash would be equal to history dot back dot, let's say first, and B dash is going to be 0, probably. B dash is going to be 0, and yes, what do I, and yes, and X is going to be 1, comma, Y is going to be 0. Okay, that is cool. That is cool. Now, int, now, int, let's call it A dash, NA, new A dash, new A, it will be equal to history I dot first, and int NB is equals to history I dot second. Okay, now that we have that, what do? We have to see which one of A and B is lower. Okay, and we can switch them. Okay, if A is lower than B, if 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 A is lower than B, then swap A and B, and then swap X and Y. Else we are good. Else we are good. Now we know that B is the smaller value. Now we know that B is the smaller value, and that is the value that we want to replace, and by how much amount. That is the value that we want to replace, and okay, int mm, neg y. Naming stuff is the hardest thing. Neg y is NA divided by NB, and y minus equals neg y. Okay, x plus minus equals neg y. So let's call it neg x, negative of x, and now my x is fine. And I would like to make my y equals 1. Y equals 1. No, no. Here when we were replacing 6 with 9 and 15, the other thing is always it has to be multiplied by, yes, it has to be multiplied by how many I do have. So neg x multiplied by how many of y I do have. And what was the name of the function? Diophantine equation dot CPP. Okay, and now that is given, multiply. This is how many new x I need. Okay, y I had, and now Y is 1. Mm, Y is Y. Y is 1 into Y. Y is Y. Y is Y. Y is Y. Y is Y. Yes, makes sense. And I have to change B to be equal to an A, new A. And now my claim, what is my claim? Now my claim is that when I come out, I should have the correct values of X and Y, which I would like to prove actually. Now in res, I should have X and Y, which I think I can replace with something like this. Let's say I have int X and Y. I think I can do this, X comma Y, deconstruct. Nope. Okay, I cannot do this. Maybe this. Okay, this is also wrong. So not city. How to construct pair in C++. My laptop is going to die in a while. This is still alive. My phone is good. My phone is good to go. I can charge my laptop now. Cool. Now it is going to live. And okay. Nope. Not like that. Okay. Cool. Now I have X and Y and C out. Let's write the whole thing. Okay. A into X, right? C out A into bracket X and closing bracket plus then B, then space. Yes, space into space, this bracket, Y, closing bracket, space equals space, the GCD of A comma B. Now cool. Now I expect this thing to work. What was the name of the program? Diophantine. Now it wants some input. Okay, this thing is wrong. This thing is a bit wrong. Yeah, 39 into 1 plus 15 into 0 does not equal to 3. Okay, so something went wrong. Our values for X and Y are wrong. Let's keep track of whatever those values were throughout. See out X, Y, and a new line. Client or slash shout 30, 39 and 15. 39 and 15. They are never. I'm changing this. Okay, after swapping NAA is the bigger one divided by P. That should not be equal to 0. Neg x should be at least 1. Right, neg x should at least be equal to 1. Okay, because makes sense. 39, 15. 39 into minus 5 plus 15 into 1 is not quite correct, but it is better than before. 39 and 15. 1 minus 1 minus 1. That is horrible. That let's output A and B. 39 and 15. Okay, because of the stupidity of human beings. Okay. And here like this, and okay, swap these two and swap these two, right? Okay. Land around 39 and 15. Okay, B underscore 8 and minus 3. 8 and minus 3. This might give an error if I give them in the opposite order. It is still cool. It still works. That that is cool. It works. That is cool. Hello, sir. I got into electronics and computing. Can can you tell me if it is a good field? If you like electronics and computing, then it is a good field. Otherwise, not. Right? If you like it and if you can make money in it, then it is good. And if you only like it and you cannot make money in it, so you should do something else on the side to make money. And if it only makes money and you do not like it, then you have to consider your options. Maybe continue with it if it makes a lot of money and you are fine with it. Yeah, those are the choices. So this function works. This function works. That is so cool. Now this thing works. This whole thing works. That is cool. That is cool. I would like to add this to my snippets. 3 hours and 14 minutes. That is cool. I would like to add this to my snippets, which uh, MRs We go here and uh, this is Diophantine. No, this is not a general Diophantine equation. Oh shit, okay. We have not done the whole thing. Diophantine. This, yes, we have implemented extended Euclid algorithm. What we still lack is a general Diophantine equation, a function that would take. So we have written something that could solve this, but we are yet to write something that would solve this. So, but we are very close. We are very close. So we can call this. This will return a pair of integers Diophantine, P-H-A-N-T-I-N-E, P-H-A-N-T-I-N-E, Diophantine, and this will take in A, int B, and integer C, and this function will or auto, not history, auto response for extended Euclid algorithm for A and B. I do not have to declare them, they are already declared. And when I have the solution, even before calling this, I have to see int G equals uh, GCD of A and B. And I need to see if there is no remainder when I divide C by GCD, only then I do this thing. Otherwise, there is some remainder, then there is no solution, and I can return make pair with values 0 and 0, which would indicate there is no solution. Otherwise, if there is some solution, then I would like to find it, and that would be very easy. I can do this dot first multiplied by C divided by G, and this dot second multiplied by C divided by B, and return rest. That is a general solution to our Diophantine thing. Now, if instead of calling extended Euclid algorithm here, instead, if we were to call our Diophantine thing with A, B, and C is going to be our third variable into A into C. And instead of finding the GCD here, we would output the client Diophantine.out, run. 39 is our A, 15 is our B, and our C is 12. And we should at the end see something like this: 39 into 2 plus 15 into minus 5, or something very equivalent that just adds up to give 15 and to give 12. Now, this is what we got, but does this thing work? If we do 39 into 32 and minus 15 into 12, that does not give us 12. Of course, that does not give us 12. This is very big. That does not give us 12. GCD of A and B. Okay, we solved this for the GCDs of A and B. And the answer we got was this. The answer we got was this. Okay, so some shit. GCD should be 3 and C is 12. C is 12. GCD should be 3 by 12 into 4. So even if we do this here, this should become minus 12 and not minus 30 or whatever it was becoming there. This is wrong, clearly wrong. Let's do see out G and see how that goes. Slash out for 39, 15, and 12. GCD is 3, which is is it the way that I'm taking input? C out C. Clang dot slash out and 39, 15, 12. That is correct. That is correct. So Diophantine, this is returning something wrong. See out res dot first and see out res dot second. 39, 15, and 12. 8 and 8 and minus 3. 8 and minus 3. Multiply these two numbers by C divided by GCD, which is GCD is 3 and C is 12. C is 12, GCD is 3. Yes. Thirty-nine, 15, and 12. 8 and 3. Okay, what am I getting here? 17, A and B. 39, 15, and 12. Wait, 8 into 4 is 32. It should be the other way around. If I do 39 into minus 3 and 15 into 8. It is in the opposite order. It is x and y are in the opposite orders. Okay, x and y are flipped due to some reason. My answer is correct, only that x and y are flipped. Why were they flipped? Because of this, because of this, because of this. Okay, I can check this beforehand. Bool order equals A greater than B. Right. 17 and at the end before returning. If not order, if they were not in order, then I would swap x and y. 39, 15, 12. It is always already out of order somehow. Makes sense. Makes sense. Okay, okay. When I go out of this loop, yeah, makes sense. Makes sense. This makes sense. Okay, this will make sense. This again and return them to their original order. No, no. Yes, yes. Now 39, 15, and 12. Maybe no. Clear, not press out. 39, 15, and 12. That is correct. If I do 39 into 12 or 15 into 32 minus 12 into 39, I get 12, which is correct. Which is correct. Shit. Okay, so now this thing works. Now this thing works. There is competitive programming. Yes, you need number theory in competitive programming. And here right now we are trying to implement Diophantine's equation solution in C++, which we read about here. Yes, so this is cool. This is cool. Now we can implement, we have an implementation which solves Diophantine's equation, which is cool. Okay. Tomorrow, Chinese remainder theorem and some other results. I don't know. I think we should not go into the why for these things because that would be research level. I don't know. But we can go into the why for Chinese remainder theorem. I think Chinese remainder theorem is not needed. I'm at 1300. I don't know. Tomorrow I will do questions. Tomorrow I will do CP31 questions. And before ending, I will add this to my snippet folder. Diophantine equation. Yes. Yeah. Copy this whole thing and here Diophantine.cpp, paste, and in my snippets, copy, paste, file path for Diophantine, and I'll also change the path here. Wait, is it not saved? Yeah, it is not saved. It is the this thing. This is not saved. That is why it was not showing there. Now it is saved and I should see it here. Suggested. It is not suggested. Okay, so something might be wrong. Tmux detach. Lua Walrus CP. I do have it. Diophantine.cpp and in snippets. And change till this, and okay, it is just not showing here due to some reason. Diophantine, and not the same mistake we made the last time. Diophantine, and yeah, Diophantine and Diophantine goes will go here. And what I'm doing right now is since I might need this code during a contest, I do not want to rewrite it at the time. So I am creating a Vim key map so that I can just press that key map and all the code would auto-magically appear there, which is cool actually, which is pretty cool. And what is the key map? Dio, leader Dio, and things will print. Uh, Print the code for solving a Diophantine equation. Okay, and we should be good to go. And if I open any file, hello.cpp, which already has some things, and I press space, let me first include some things using std, using namespace std, and include bits slash stdc plus dot h. And here, if I do space dio, the whole code is here. I can just call this Diophantine thing. Now, let's say I need to find, let's say I have an equation where a equals the same thing, a equals this 39 and b equals 15 and c equals 12, and I need to find the solution to this Diophantine equation. I do not have to write the whole code from scratch. I can just do space dio. The whole code is here, and I can just call the function Diophantine function with a, b, and c, which is very cool. Store it into a pair. This is cool. Yep. Vim is cool. Vim is pretty cool, pretty fucking cool. And so today, what have we done? We implemented, first of all, we implemented this thing, which took quite a bit of time. The way to find modular inverse. We did that. That took a lot of time. And then we did some theorizing in which we calculated we figured out how we can calculate, how we can find Diophantine's equation, solution to a Diophantine's equation. But still, there is something that I do not get, which is this. I do know that there would be an infinite amount of pairs, but how would that be? I'm just adding this and subtracting that. Okay, what does this mean? Any solution where k is an integer. If k is an integer, okay, so what I want in this is a into this thing. Okay, shit. Okay, this makes obvious sense now. Okay, we are saying we have a solution where a into x plus b into y equals c. And we are saying that there is an infinite pair of x and y which satisfy this given condition. And we are saying if we have some x, then we can do for some integer kx into a divided by GCD of x, GCD of a and b, GCD of a and b. We are saying that we can replace x with this thing, and we are saying that we can replace y with a with y minus ka kb actually into GCD of a comma b, and this would still be true for this equation. Why? Because x is being multiplied. This should be b and this should be a. This is b and this is not b, this is a. And now since x is being multiplied by this thing, so let's say we just multiply a with this extra bit that we added, and this would result in k into a into b divided by, because we have ka kb here, and kb multiplied by a is kab divided by gcd of a and b, and we multiply b with this extra bit here, which would be k a and b ab divided by gcd of these two, and this is negative, and these two values are same, so they cancel each other out, and our solution still holds. That is true. But now the thing is, would this always return in an integer? That is the question. Yes, this would always be an integer, because we have something like a into k divided by GCD of a and b. Since this is GCD of a also, this thing will always divide a. So this thing always will divide a. So we would have k, which is an integer, some factor of a into some factor of a, which would be an integer. So that is cool. And this thing works. And it has been 3 hours and 37 minutes, which is quite a bit. And I would end the stream now, and maybe I can go and do some calisthenics, which would be cool. And today a lot of people watched my video, which is cool. And thank you for being here. Bye.